that future expectations play a role in how people make decisions today, which is a key component of DSGE models. So it was the choice. So what should we have done? The Fed, that's not what the point of this. It's not to say that they shouldn't have lowered their target inflation, because there was other research that showed that the main reason for why they may have done that might have been to prevent a liquidity trap. And yeah, so that's it.
All right. Okay, thank you.
Okay,
I'm sorry I gave you a hard time, but
no, I understand that. That's my fault, but
yeah, you know you get 8 minutes, right? So
yeah, I did.
You should have like prepare. I mean, more accordingly with the time, like putting your different sections for your presentation. So that is. So did you rehearsal your talk? I mean, before you, this is your first time presenting, or?
I mean, I went over this myself. I guess my issue was I got caught up in the beginning, because there's certain things I need to explain for most of it to make sense.
Right, I know. So because
then I get caught into the weeds of all those different aspects, and I just lost track of time.
Right. So 8 minutes is something is short. So if you feel that you still need to express more, just feel free to make an appointment with me so that you can explain to me. All right.
Okay.
Right. So that you can make full use of the time. And I'm sorry, I have to really enforce the time constraint so that we can move on. Right. Okay. Thank you.
I understand. Thank you.
Congratulations. So let's move on to our third. Is there any questions?
Oh, yes. Where would you study something like this? Would be in an advanced economics class?
Yeah. You could take it. It would have to be like an advanced macroeconomics class, because they don't touch on DSGE models in your intermediate macro courses. They might explain some of it, but you'll never see it, because it requires more sophisticated math.
All right. So Keenan, you are on.
Thank you.
All right.
You are the co-host, so you know what to do.
Yes. Sorry, 1 second here.
So Keenan is gonna tell us about the Kepler's law.
Can you see my screen?
Yes.
Okay. So let's go. Here, 1 second. Okay. I apologize. So I did my project on Kepler's laws for planetary bodies following hyperbolic trajectories. More specifically, I wanted to see if Kepler's laws were preserved for planets following hyperbolic trajectories. The motivation for this came from in class when we talked about Kepler's laws for orbits, like circular orbits and elliptical orbits. I just kept wondering if these things were still true for planets that followed a different path, or a satellite that follows a different path.
Keenan, which class?
This class, mathematical modeling.
Okay.
So to begin, we're gonna recall Kepler's laws of planetary motion. The first law is simply that the orbit of a planet is an ellipse with the sun at one of the two foci. The second law, a line segment joining a planet and the sun sweeps out equal areas during equal intervals of time. And the third law, the square of a planet's orbital period is proportional to the cube of the length of the semi-major axis of its orbit.
So is this something about the solar system?
Yes.
Okay.
So what do I mean by hyperbolic trajectory? I'm certainly not talking about a planet that is following both of these curves at the same time, or a planet that is jumping between these. I'm specifically talking about a planet that follows one of these curves. So what exactly is a hyperbolic trajectory? Firstly, the words orbit and trajectory both refer to the path of a body traveling through space, but these things do differ. Often, orbit is used when speaking about paths that have some sort of a repetitive characteristic. Take, for instance, a circular, elliptical, or even parabolic orbit. I include parabolic orbit because theoretically, if you had infinite time, the planet would just rock back and forth along this line, even though that would never actually happen. However, a hyperbolic path is not repetitive. The body will never return. That's why we refer to it as a trajectory. And then, as you can see, the parabolic case can be thought of as the borderline between the two. So how is a hyperbolic trajectory achieved? For a hyperbolic trajectory, the eccentricity E must be greater than 1. This eccentricity is given by this simple equation where you take O, which is just the focus, and P, a point on the curve, and you find that distance and compare it to, and you can divide it by the distance between that point and the closest point on the directrix, which is this dotted line that you see here. In the context of true hyperbola, this line would be between the two hyperbola, or the two sides. And then, so how might a planet or a satellite travel along this curve? Well, it has to go faster than the escape velocity to travel along a hyperbolic curve. And so some of the bullets I wrote down that you could achieve this if we imagine that all of the sudden the sun lost half of its mass, we would fly away in a hyperbolic trajectory because there wouldn't be enough gravitational force keeping us confined to its orbit. Another example would be if Earth all of a sudden picked up in speed drastically, besides how bad that would be for humans on Earth, it would also send us off in a hyperbolic trajectory. And then finally, if the sun were to spawn much further away, the gravitational force would be much weaker and we would fly off again in a hyperbolic trajectory. But basically, you're just trying to manipulate these variables so that your speed is greater than the square root of 2gm over r, where g is the gravitational constant and m is the mass of the object you're orbiting.
Okay, I have a question.
Yes.
When will we move along a parabola then?
Along a parabola?
Yeah.
Okay, so for us to move along a parabola, we have to meet a very, very specific case where the distance between, say, the sun and the curve that
geometrically, I know geometrically what parabola is, but you were giving different scenarios. How can the Earth escape using hyperbola? For example, the sun drops his mass, I don't know how much, and blah blah blah. What about the parabola? What should happen so that the Earth starts moving along a parabola? Not hyperbola, but parabola.
So we would just have to achieve an eccentricity of E. And so the way that we would do that is by satisfying the equation PO over PA. And you can do that a number of ways, but I don't have the exact measures.
Okay, so you are saying eccentricity has to be 1.
Yes.
In order to, okay, good, thanks.
You're welcome. Okay, so moving on. Kepler's first law is not preserved. Kepler's first law states the orbit of a planet is an ellipse with the sun at one of the two foci. This law is not conserved as a hyperbola is not an ellipse. That's not very interesting, but it just happens to be a fact of how it is. And also, planet following a hyperbolic curve is not in orbit. It's following a trajectory. There's no phase. Kepler's third law is also not preserved, and this one actually fails a little bit more spectacularly because Kepler states the square of a planet's orbital period is proportional to the cube of the length of the semi-major axis, and the semi-major axis of a hyperbola is negative. So you're saying the square of something is equal to the cube of a negative number, which is obviously not true. And then also, I just wrote that a planet following a hyperbolic trajectory does not have an orbital period, which is another reason that that's why this law. And then what about Kepler's second law? Kepler's second law, the one about sweeping out equal areas in equal times, this one does in fact hold for planets following a hyperbolic trajectory. So first we have to use some equations, and I warn you that the math gets pretty unexciting because a lot of these variables depend on a orbital phase, but there is no orbital phase for a hyperbolic trajectory. So this term mu turns into a 0, and then the r, which depends on mu, is 0, has a 0 in the denominator. So they just model this by putting a big old 0 there and moving on with their lives. But the energy integral is a constant, and that's important.
So 2 more minutes.
Okay. So explanation of why Kepler's second law is conserved, is preserved, I meant to say, I'm sorry. The preservation of Kepler's law, hyperbolic, really boils down to the equation that was on the last screen, which simplifies to become E over V squared with the subscript infinity, which is just notation used to explain that this satellite or planet or whatever you're modeling is going to just fly off into space, never return, divided by 2. And an interesting consequence is that the satellite following this curve will have the same speed coming in as it does leaving. So if you can imagine the bottom of the hyperbola is like a vertex. If you go on the same distance of each side of that vertex, then the planet will be traveling at the same speed. I just thought that was cool. And then this equation is used to sometimes find the velocity of something while it's flying by. And then the consequence of this energy conservation is that angular momentum is conserved. And so angular momentum is just mass times velocity times the distance between the centers of the two objects. And this has the effect that equal areas are swept out in equal times, even though it doesn't sound as exciting as Kepler's quote. And then finally, Newton revised. I was going to include a slide of how you could work on this to make it better, but Newton did that himself. So his first generalization was that shapes of orbits are conic sections and the center of mass is at the focus. His second generalization is that orbital motions conserve angular momentum. And the third is that the proportionality between the square of the period of the cube of the semi-major axes now depends on the mass of the two bodies, which also fails for hyperbolic trajectories. And the last slide is just my sources.
Any questions?
Okay, go ahead, Professor Yuto. Okay, I have 2 questions basically.
Okay.
One, this is studying the inverse square law with Newton's law of gravitation, but that is only a first approximation. Have you looked into, any relativistic aspect of this? And secondly, did you also look at other, inverse laws as opposed to say 1 upon r squared?
I did not. And then what you're asking about, the first question.
Okay, let me rephrase the question. I like this topic, and when I was an undergraduate, I did same thing, orbital motion, but I considered things beside the inverse square law. like inverse cube law, what happens 1 upon r, 1 upon r to the 3 upon 2. So that's something that brings out other interesting aspects. And then since we live in a real world that is governed by relativistic, relativity, the Einstein theory of gravity, it would have been nice to compare what happens in that situation with what happens in Newton's situation, because little things happen like Mercury's orbit and so on changes, it precesses. So these are important things because they are real and they're not just theoretical. So
I agree, and I think that would have been interesting. I didn't do that because what I was considering when I did this was I was referencing our textbook, and I wanted to know specifically, can I extend what I see right here in front of me in this textbook to deal with maybe a hyperbolic trajectory? And it never crossed my mind to try to look into other scaling laws. I was only concerned with that specific model that was in the book.
Well, it's something for the future.
Yeah.
Thank you.
You're welcome.
Kyle?
Yes, hello, can you hear me?
Yes. So I think you are the co-host, huh?
All right.
Yeah, you are now.
All right, let me just make sure. Can you see my screen?
All right, good.
Wow.
I just want to make sure. So do you just see the title slide right now? I just want to make sure
Yeah.
everything's.
That's what I see.
And also, I also want to. You see a red dot,
Yes.
and is it moving smoothly along the screen, or is it
That's
jumping
kinda
around
jerky.
everywhere?
I have to confess, the title is very intriguing.
I hope so. I found it intriguing. That's why I decided to talk about it. So
Okay.
my name is Kyle Leibovitz, and I'm here to talk to you about the statistical mechanics of money, income, and wealth. So before I get started, I want to give credit where credit is due. Most of this presentation is based on this man's work. Mr. Viktor Yakovenko wrote a paper on it and actually goes into more depth than I'm about to go into. So outline of this presentation, I'm going to talk about a brief overview of statistical mechanics and its theoretical applications to economics, and the data found and what was how it relates to the theoretical applications and conclusions derived from this data found. So we're going to get familiar with these two distributions, the Boltzmann-Gibbs distributions, Pareto distribution. The main thing to note is that the Boltzmann-Gibbs is exponential, and the Pareto distribution is based on power law scaling. And this is a brief overview of statistical physics, just very, very brief. So imagine you have a room. You see the slide is zoomed in. So imagine you have a room where you have a gas and the molecules, they have energy in them, and they all start out with the same energy. So when the molecules collide, they actually transfer energy. So one gains energy and one loses energy. And we're assuming this room, of course, is a closed system, which is shown here. So energy is conserved, whether they, from their starting energy to the energy they have. And this is actually observed in physics, that it follows an exponential distribution, or the Boltzmann-Gibbs distribution here. And this is stabilized because entropy is maximized, and this is pretty much confirmed. So what happens if we actually change energy with money, and instead of molecules, it's people? So what happens is a transaction occurs where, let's say it's a buyer and a seller, and a buyer would lose money and a seller would gain money. So what happens is, and the money conserved in the system. So of course you can make the proposition that this trend would follow an exponential distribution, or the Boltzmann-Gibbs distribution, which would look like this. This is what an exponential distribution looks like, but there's a problem with this graph in that you can have $0, which doesn't account for debt, which doesn't happen in the real world. So it builds up along the zero, because once you have $0, you can't make transactions. You can't gain money or lose money. So how do we apply debt to our model? We do that in two ways here. The first way would be by limiting the total debt or limiting individual debt for everyone. And this model shows limiting individual debt by 800, which just spreads out the curve. It doesn't really tell us much. And individual debt isn't really restricted like that, but we could restrict the total debt with this concept of the required reserve ratio, which just limits the amount the central bank can loan out to people. But this concept also really isn't enforced in the real world because there are things like investment banks and hedge fund management that doesn't have a required reserve ratio. So money kind of moves differently. So with this in mind, what have we observed in the United States? We've observed that this is the income distribution based on the US Census data as shown here, and it follows an exponential distribution pretty well. And even according to the log linear scale, which shows the exponential distribution is a straight line over here, the points fit on pretty accurately, but this doesn't tell us the whole story because the annual income only goes up to 120,000. But this model or this graph shows a bigger picture of what's happening. So for around 97% of the population over here, it falls on an exponential curve. And for the top 3%, it falls on the Pareto distribution or power law that I discussed earlier. And the intersection of this point is around $120,000. So people making below $120,000 fall in the exponential distribution. Of course, this is in 1997. It could be higher or lower today. And so, yeah, if you look closely, it fits pretty much almost perfectly. So this divides the classes into the lower class, upper class, where the upper class would be in the power law tail, as I would call the Pareto distribution, or the exponential tail. And the way they make their income is also different, but I might have to skip through that for the sake of time. And it doesn't apply to just that year, it applies to multiple years. This is over 18 years. So if we look here, this is rescaled to adjust for inflation and value of the dollar. And if you see here, it's pretty stable for the individual income of people, this income distribution, but the upper tail actually deviates significantly. And there's plenty of factors or variety of factors why that happens with bubbles and crashes. And we'll get into that, hopefully if I have time. This is how you would, so if you look in the previous graph, you can't really model upwards of into like people making 100 million or $1 billion. So not all the data is actually modeled. So we do that with this, the Lorentz curves, which essentially reparameterizes the data so that just about all of the income is represented in the form of a percentage. And this is how it's reparameterized. It's cumulative percent tax returns and cumulative percent of income shown here. And you could actually measure the amount of inequality using the area between the curve and the diagonal. And the diagonal actually represents equality, perfect equality in the system. And if you look closely at the very right side, the curve actually hits the right side of the graph and then spikes up, which is evidence of the power law tail I mentioned earlier. So income inequality over time in the USA. So income inequality is actually based a lot mostly on the upper class or the people making over $120,000. And you could see their share of the wealth, which is represented by F here. Hold on. It's represented by F here. It rises during speculative bubbles. So in 2000, it rise during the dot-com bubble. And in 2008, it rise during the housing bubble. And then subsequent crashes causes their share of wealth to go down, which causes the income inequality to go down. And this dimensionless parameter here is actually corresponds to the power law tails, to the power law tail. So the more it decreases, the more they have the share of the wealth, which means, as you can see here, there's a trend going downwards. So income inequality is of course increasing. And you're probably wondering, we went over just the United States and if this applies even to other countries. And well, here's an income distribution of the European Union, and around 97% of the curve actually falls in an exponential distribution. And here's just a breakdown of the countries in the European Union. And this is actually pretty recent data. This is 2019, and it fits pretty good. This is also for various countries in the journal, or in the studies, around 67 countries, so European. So my conclusions. So what we got from this, of course, is that the significant amount of the population actually falls into an exponential distribution, which before this paper wasn't actually found to be, or it wasn't actually recognized or observed beforehand. The power law was actually used to describe more the upper class and all that. And the exponential distribution is actually very stable, not just for the United States, but for everything else in general, or for every other country in general, excuse me. And why does this stuff matter? So this is actually the first step in understanding the correlation between physics and economics, and modeling this, or showing the correlation mathematically like this, and showing that you could relate molecules in a gas to money in an economic system actually can show great potential for the development in this field, and for modeling or for rigorously analyzing the financial markets through statistical physics, which is what's being applied here. And honestly, I believe that this field can actually develop into a standard in the economics course curriculum. And it's possible that even combined with game theory and psychological economics, you could potentially forecast financial trends much more accurately than what previously thought. And that's the end of my talk. Any questions?
Okay, so technical question: how you feed the data to an exponential curve?
To fit the data into exponential curve, so it's just proportional to the exponential curve to fit it exactly. So the equation, of course, is right here.
Right,
so the
yeah.
parameters are always different, or of course
So
have to be.
basically, you want to find what t is, right?
Yes.
Right. How you do it?
To find t.
Yeah.
So t is the average income per person. So you would just, yeah, t is the average income per person, and r is the actual income. So it's proportion, or it normalizes it to fit the curve. This one actually in the paper, even the person
You remember we had a homework on this, right?
I don't recall.
You don't recall? All right. So I'll
actually
homework then. I think I give you 15 points for the full credit. So now you just give me a reason to double check your homework.
I might have to.
Right. So actually, this is the second set of homework. So I give a table of data, and so we suspect the data are from exponential curve with a times e to bx, and to find the a and b. Remember that?
I vaguely remember it.
Okay.
Vaguely.
Okay.
It's been a while.
All right. Okay. So good talk. So let's move on to Nicholas. Where is Nicholas? Are you here?
Yeah, I'm right here.
Oh, wow, you're all dressed. Okay, you are co-host. Now you can share your screen.
All right. You guys see it, right?
Yeah, we can see you, but your slides.
Yeah.
Oh. There we go.
Okay, good.
Can't start my slideshow. All right. So my project's on the logistical growth model. However, those parentheses, not parentheses, the quotient marks are there for very important reason. I ended up abandoning that topic, but I'll show you guys how I transition to that now. So initially, my idea was to try and model the growth of cities or empires, such as like the Romans or the Mongols, using the logistic growth model and allometric exponents. I started trying to do that because I saw roadways as vascular networks, trying to connect resources and nutrients to different parts of the city. And what I was going to try to do was show how the ratio for I rehearsed this like 4 times. Basically, I'm just gonna keep going. Roads are self-similar. I realized that initially I didn't think they were self-similar because of different lane changes, and so self-similarity in terms of the textbook talked about capillaries having the same area preservation model so that they can serve and produce a smooth fluid flow. But trying to model the growth of cities using a logistic growth model, I ran into a few problems, notably that people and resources aren't fluid. You know, they make their own decisions. So for example, like a body of fluid dynamics, so if water just goes where it needs to go in terms of where gravity's pushing it or wherever the system is pushing it or telling it to go, but people make their own decisions, so they can't be modeled that same way. More importantly, though, I realized that vascular networks for biological systems service a 3-dimensional body. And by that, I mean that cities are quote unquote 2-dimensional. And by that, I just mean that right here. Oh, that slide got messed up. I'm sorry. So I ended up trying to solve the volume preservation model. And through that, I ended up getting to traffic. And that's what I ended up doing my project on. My intentions were to try and come up with a traffic model that would mitigate traffic, obviously. But wow. So why does traffic happen? In a perfect, so if cars were autonomous, they can brake and stop in front of each other like perfectly. So they'd kind of be working with like a accordion effect. But people aren't perfect, and competitive driving can lead to non-linear interactions between the vehicles, which in turn create a non-equilibrium system, which basically means that the rate of resources being passed around is mitigated. So now I tried to start trying to model some traffic. So these are some definitions that you're gonna need to know for this. Jammetons are pretty much traffic jams. So when you're trying to go down like 8th Street and you're just going for 15 minutes, just slowly, that's a moving traffic jam. So jammeton is a moving one. Soliton would be looking at a jammeton at a particular instant. So instead of modeling it over time, you'd be only looking at a specific portion of it. And so the first non-equilibrium model I found for traffic flow that wasn't entirely physics-based was the Payne-Whittam traffic flow model. The basic relation is that the flow rate for cars is directly proportional to the travel speed and car density. By car density, I don't mean the mass and volume of the car. I mean how many cars are on the road. But there's a problem with that. This initial basic relation is for equilibrium, and evidently traffic, is dynamic. So we won't have the same traffic at any given point of the day or any other day. So this was the equation that I found for traffic acceleration that could be modeled using a non-equilibrium model. I was able to find, I wasn't able to do any of this, by the way, I read it. We can rewrite it as this system down here, where C naught is the traffic sound speed and tau is the relaxation time. And by relaxation time, it's just the best example I can give you is like when you're at work and you wait an extra 15 minutes for traffic to die down, that's relaxation time. So I needed to solve the homogeneous portion of this equation simply because I couldn't do the non-homogeneous. I don't have enough math, but thankfully I knew how to do this part. All you have to do is set U equal to the state variable for P and Q, and then find a Jacobian, and you'll get these two eigenvectors, eigenvalues down here. The important thing to note about these eigenvalues is that they're directly proportional to velocity. And that is where I came up with the next portion of my presentation.
2 more minutes?
Yep. All right, so as I said, the most important part about the eigenvalues that I found after solving the homogeneous equation was that it's directly proportional to velocity. By solving the Riemann problem, which is something I couldn't do, I needed to look it up. We were able to apply this same traffic model to non-homogeneous roadways. So basically, we can still model actual traffic jams instead of just a particular fluid flow using this equation. So I needed to maximize the efficiency of our roads, and I came up with using 3-day space. So my idea was that flying cars, pretty much. So with a 3D traffic check system, obviously we can't have lights. That completely defeats the purpose of going up in the sky because we're trying to avoid traffic. There's also problems with airspace and airports. And if you live like in an area like Brickell, for example, you obviously can't park your car. If everyone has to go and park their car in the same garage, then you're still gonna have to go through a traffic jam. So the solution I came up with was a Mobius strip virtual highway over the entirety of like South Florida, with the airport centered at the middle. The reason I chose a Mobius strip was because it could allow me for laminar flow going through all the cardinal directions. So if it was technically wide enough, and including the area in the middle for the airport, if it was wide enough, then we can accommodate enough vehicles and have enough of a area covered that we can just continue to have a circular loop all going in one direction instead of having to stop at lights over and over. So cars would just go up, enter it, and get back down off of it. One of the problems with the Mobius strip, obviously, is that you'd be flying upside down at some point. So just rotate the car like a jet. If you miss an exit, you can't turn around on the turnpike. So just go all the way around again and get off the right time. And in retrospect, there's obviously no real application to this 3D traffic model in our current time. We don't have flying cars. That's obviously not a thing. I ended up coming here just because, I don't know, I can't. I go from one topic to the other, and as I keep doing research, I would get absorbed into another thing. With that, I wanted to ask if any of you guys had better ideas for shapes other than a Mobius strip.
Klein bottle.
All right.
What is that?
What?
What is a Klein bottle? Or
Well, there is Wikipedia for that. It's a long story.
Could you put it in the chat?
Klein bottle?
Thank you, by the way.
Okay, great. Klein bottle, yeah. Right, a bottle never full, huh? Okay, great. Yeah. I think we do have flying cars, right? I believe Honda, I watch a video sometime. Honda has invented a car that can fly and drive. It's a prototype, probably. Yeah. Right.
Flying cars, I understand, but Möbius list, it will be much harder.
Right, so I believe I skipped Michael. But here I have another, actually I have a group presentation by Sarah and Lily. They kind of have a emergency. They asked me if we allow them to go before you. Is that fine with you, Michael?
It's totally fine with me. Totally fine with me. I'm not ready to get ripped apart.
Right. So Sarah and Lily, you can go now. So who will be doing the slides?
Me, Professor.
Right. So I'll make you co-host.
All right. Let me share my screen. Whoop. All right. Whoop. Here we go. And Lily, whenever you're ready, let me know when to go on to the next page. Can you guys see just the front, like just the thing? Is good?
Yeah.
Okay, so we did our presentation on 2 models of epidemiology, and we used Bernoulli's model and the SIR model by Kermack and McKendrick. So this is important, obviously, in today's world because of everything that's going on with the virus and everything. So we will look at Daniel Bernoulli's smallpox model and the SIR model based on Kermack and McKendrick's theory of infectious disease. Smallpox, if you don't know, is an infectious disease that affected many people around the world. And variolation involves taking infectious material from an infected patient and infecting a healthy person through a scratch so that they have like a milder infection and develop some sort of immunity to it. Many people did not know how to feel about it, so that's why like Daniel Bernoulli and Kermack and McKendrick even began to do this, because they wanted to see if it was good or not. So further, Bernoulli decided to study if variolation was beneficial. And he did this by calculating the increase in life expectancy if smallpox could be eliminated as a cause of death. Bernoulli showed in his model survival rates from an actuarial life table, which we will show you, made by where Bernoulli calculated ages starting from birth to 25 years and the fraction of each population never did by the smallpox. He kept track of 13 new inoculated at birth. So here, we just, like, this is our little table we made. So this is the ages by years he calculated, like I said, 0 to 25. On the next slide, we'll have 14 through, to 25. But go back for a second, just to show, like this, it's the natural state with smallpox and then the state without smallpox. And then like the difference or gain of his experiment. So you see like the gain is increasing. If you go to the next slide. So for ages 14 through 25, once again, it is increasing. So this is a graph. This is the so this is the natural state with smallpox and the state without smallpox and with the difference or gain. So we see that the red is the natural state with smallpox, The green is the state without smallpox, and then the yellow is the difference or gain that we have.
Yeah, this is just the I did this on Excel. I put the life tables so that we could see it a little bit more graphically,
Like,
the difference.
yeah, like in a different perspective. It's basically
Instead of
stating the
just
same
number.
thing as a life table, is just maybe like in a more clearer view. Okay, so now we're talking about Bernoulli's representation on the vaccination of smallpox. So in Bernoulli's model, I'm gonna tell about the variables so we know what the equations mean. So we have any age A, where lambda of A is the rate of infection of susceptibles. I have such a hard time pronouncing that. All right, and S of A is the rate of recovery among the infected, and U of A is the rate of death unrelated to smallpox. So in this way, the U of A defines the probability for a newborn individual to be alive and susceptible at age A, and WA represents the probability to be immune and alive. So if you didn't know, just to let you know, the susceptibles are people who are more likely to get smallpox. So that might be because you are in bad health or you're older, things like that. So the derivative we show is that first equation, and then the derivative of u, and then the derivative of w is the second equation. And we will set the initial equations both at 0. So we input 0, and for u of 0, it equals 1, and w of 0 is going to equal 0. And those are the differential equations to represent Bernoulli's model. Okay, so like I said, we're using those initial conditions because all newborns begin life in the successful class and can be solved with the integrating factor at it's like a T. Sarah, what's that symbol?
Tau.
It's a
Tau. Mm-hmm.
Tau. So then we have the exponential of the integral of lambda of tau right there. And then we're trying to get to u of a. So then we take the exponential again, and the upside down v is the integral of lambda. And furthermore, that's how you get capital M of a as well.
The upside down V is called lambda.
Lambda is in the integral. The one where I say where
it's a capital lambda and a little lambda.
Like the upside down W. It's called omma.
Thank you. I appreciate that. So it's a capital lambda. Okay. All right, let's continue. All right, so we'll substitute u of a into the derivative of dw over d of a, or dA. And with the integrating factor, we will get this equation right here. And here's a little graph just showing the survival probability rate. And the function is L of A equals U of A plus W of A. So the probability of survival through age A is given by the survival function, which is right below. I said L of A equals U of A plus W of A, where U of A is the proportion of newborns that will remain alive and never infected, and W of A is the proportion of those alive with immunity. So essentially, it is impossible to completely eliminate smallpox. However, in Bernoulli's model, the analysis led him to suggest the inoculation of all susceptibles, where inoculation is the method to artificially induce immunity against infectious diseases. So Daniel Bernoulli once said, "It is then only the risk which is attributed to inoculation which should keep us undecided. What would be the state of the human race if at the price of a certain number of victims, we could procure for freedom from natural smallpox?" So therefore,